In this video, we're going to develop the definite integral by looking at this example, and then we will look at the fundamental theorem of calculus. So in this example, Soulful Scents has found that the marginal cost of producing X ounces of a new fragrance is given by C prime of X equals 0.0005X squared minus 0.1X plus 30, a function that's valid for X less than 125, where C prime of X is in dollars per ounce. Okay? What we want to do is use integration to find the actual total cost of producing the first 100 ounces of the fragrance. Okay, so we know that marginal cost is the derivative of total cost. So now what we need to do is go backwards from that and anti-differentiate to go from marginal cost back to total cost. So the total cost function C of X is given by the antiderivative of the marginal cost function. So it's given by the antiderivative of 0.0005x squared minus 0.1x plus 30 dx. Okay, so anti-differentiating that, we split it into three antiderivatives and pull out the constants. So we get 0.0005 times the antiderivative of x squared. Add 1 to the exponent to get 3, so it's 1/3 x cubed. Then the antiderivative of the next term is minus 0.1 times the antiderivative of x to the first is 1/2 x squared, plus the antiderivative of 30 is 30x. And then we have our constant of integration, which I'm going to call C sub 1, just because I'm using capital C to represent the total cost function. So this capital C out here is the constant of integration, which is different. You could call it maybe C sub I, constant of integration or something. Okay, so we know this is the total cost function. The problem is we don't know the constant. Okay, but what we could do is find the total cost to produce 0 ounces of the fragrance in terms of the constant of integration, and we could then find the total cost to produce 100 ounces in terms of the constant integration, and then subtract to get the difference, the actual total cost. Okay, so total cost to produce 0 ounces, that term is 0, 0, 0, we just get C sub I, the constant of integration. And the total cost to produce, let's see, 100 ounces, we're going to need a calculator for this, so it's 0.0005, this 1/3, or times the third I'm going to write as over 3, times 100 cubed minus 0.1 over 2, just combining those two constants there, times 100 squared plus 30 times 100 plus that constant of integration. Let's get a calculator going here and approximate that value. Since this is an applied problem, we'll just go ahead and round to the nearest penny. Okay, so we want 0.0005 over 3 times 100 cubed. Move this over now. Okay, minus 0.1 over 2 times 100 squared plus 30 times 100 to get 2,666, if we round to the nearest penny, 0.67. So that's about $2,666.67 plus C sub I, that constant of integration. Okay, so we don't know the exact total cost to produce 0 ounces, which in other words would be the fixed cost, because we don't know the constant, and we don't know the exact cost to produce 100 ounces, but also because we don't know the fixed cost. But we do know that the difference between producing the first 100 ounces and 0 ounces will give us the actual total cost of producing the first 100 ounces. So, and perhaps I should have put producing the first 100 ounces. Okay, or we could even add into the original problem here, not counting fixed costs. Might make it a little bit more clear. There we go. Okay, so then C of 100 minus C of 0 is going to be 2,666.67 plus c sub I minus c sub 0, the constants of integration, which is equivalent to the fixed costs here, cancel. So we get that the net change in the total cost to produce the first 100 ounces is that amount. Okay, let's do some different numbers here. Instead, let's look at, so let's say we're currently producing 100 ounces. What would the net change in the total cost be if they increased production to 125 ounces? Well, let's compute C of 125. Okay, plugging in up here, it would be 0.0005 over 3 times x cubed is 125 cubed minus 0.1 over 2 times 125 squared plus 30 times 125 plus c sub I. Again, we'll need a calculator to approximate that there. Okay, so my first term was, let's see, 0.0005 over 3 times 125 cubed minus 0.1 over 2 times 125 squared plus 30 times 125 comes to 4074.27. Make sure I wrote that correctly there. 4074.27. Okay, $4,074.27 plus the constant of integration or whatever the fixed costs are. So therefore, the total net change in total cost, it's your total cost when you're producing 125 ounces minus your total cost when you're only producing 100 ounces, which gives you, let's see, 4,074.27 plus the fixed cost, that's minus fixed cost at a C of 100 right here, 2666.67 plus C sub I. Well, if we distribute those negatives, the negative across the second term there, the C sub I's cancel. Like that. And so we get the net change. Well, for that we need to subtract, so let's say that previous answer minus 2666.67 gives us 1407.60. So that's how much your cost would increase. So if you're asking how much would it cost us to increase production, this is your answer. Now that's not the total cost to produce 125 ounces, but that's how much more it would cost if you're already producing 100 ounces and you want to increase production to 125. So this brings us to the fundamental theorem of calculus, okay? So if f of x is a continuous function on an interval from a to b, where a is less than b, and capital F is an antiderivative of little f, then what's called the definite integral is defined as the integral from little a to little b of f of x dx. It's defined as that antiderivative capital F of x evaluated at a and b and then subtracted. In other words, capital F of b minus capital F of a. Okay, so this is called a definite integral. So notice this is essentially what we did in this previous problem right here. We found the antiderivative of marginal cost to get the total cost function, and we've evaluated it at both 125 and 100 and subtracted the values, just like f of b minus f of a, to get the net change in the total cost function, okay? So this is how a definite integral is defined. Okay, some terminology. Little a there is called the lower limit of integration. And little b is called the upper limit of integration. I'm going to abbreviate upper LOI, limit of integration, okay? And what does this represent, okay? What does this definite integral here represent? Well, it represents the total amount of capital F, that is the antiderivative of the little f, okay, that is accumulated by let me rewrite that. The total amount accumulated by capital F would be a better way to phrase it. So it's the total amount accumulated by that antiderivative as x increases from a to b. And that's the fundamental theorem of calculus right there.